Good morning, I'm Roland Larsson. I'm working at Luleå University of Technology. And this video is about how to predict wear. It's not very easy and it's not very accurate normally to do that, but I'll try to explain what we can do at the moment. So let's go.
So why do we want to predict wear, or why do we want to model and simulate wear processes? Well, it is, of course, normally cheaper to do simulations than experiments, and it's also normally faster to do that than doing the experiments. And of course, this is what you have seen during the past 30, 40 years, that computational engineering has been growing very, very much. So you simulate a lot nowadays before during the design of a machine, for example, because it is cheaper and faster. Unfortunately, in tribology and especially in wear, we don't have the very good tools yet. So it's not yet both cheaper and faster, but to some extent we should of course do simulations or predictions also of wear. And it is a kind of aid of the machine designs if we can compare a number of design alternatives in a short time. Without, if you want to make an experiment with many different design alternatives, it will be very, very costly, of course. You may also use simulations of wear inside a running machine to use it for diagnostics. If you measure what is going on, if you measure the load, the speeds, the temperatures, etc., you may say something about the machine health. It should be written health there. I'm sorry for that. So this is something very up to date nowadays. It's you may have heard the word digital twin. So if you run a model at the same time as you run your condition monitoring software, you may do some online diagnostics of the machine health. So it's of that reason it's also important to learn how to predict wear. So, but why not? Why shouldn't you predict wear? Well, it's, as I already indicated, it's not yet very accurate. You need a lot of input data that is empirical and very specific for one case, and it's many times it's also hard to find the data itself. And the tools are not readily available. So, as I said, the models are not that very good, and the tools to do it in a very detailed way are still on a kind of research level, I would say. And in sometimes you may require very complex models, and this saying about cheaper and faster than experiment is not really correct. It's not cheap and fast anymore. So this is an area that is still under development. I would say that at the moment, this is 2021 actually, and I believe in the coming years we will see much better models. In the next 10 years we will have much better models. So it's an ongoing research area here at Luleå University, but also elsewhere. What do we then want to know? Well, we want to know how a wear and if a wear scar is formed. We want to see how the contact conditions change with time, because if we wear the surface, the contact pressure will not be the same. As you recall from the contact mechanics videos, the contact pressure is very sensitive to the micro shape of the surface, micro variations of the surface. So if you wear a scar on the surface, you change completely the contact pressure. Then you also change the temperatures, especially in a sliding contact. So we wanted to learn then how this wear is progressing, and that's a kind of aging of the machine component. we, especially now when we talk about circular economy, we really want to be better to learn about how the system is aging, because we want to have a very, very long service life of our machine components nowadays. But we also want to determine the risk of catastrophic wear. When we design a component, we really want to avoid early wear. It could be dangerous also for the machine and for people working around it. We may also use simulations of this type to learn about the influence of the initial surface roughness and how the surface roughness changes with time, how it runs in. So that could also be something to learn from that. And finally, if possible, it would be very nice also to simulate how tribofilms are growing on the surface. That is definitely a research issue at the moment. So we will be better on this in the coming years, but at the moment it's only on the research stage. But I will mention in the end of this video a little bit more about what is going on the more research level, but I will start with the very basics about wear simulations, and then you end up with the Archard wear equation, which is the equation people are referring to when we talk about wear predictions normally. Archard was active in the 50s, 1950s, and it's an elegant theory, and he assumed that you had a collision between two asperities. So surfaces, when they come into contact, there is a number of collisions taking place between an asperity and another asperity. So this is a kind of a contact between the two asperities, and they have the same radius a, and they pass each other like this. So the highest load the asperities can carry is the area of contact, which is pi a square, multiplied by h, the hardness. And now we assume, as we have been doing now a number of times in the contact mechanics, also we assume that you have a plastic deformation, which you have, of course, when you have a wear taking place there. So the load carried by the asperity is simply pi a square multiplied by h. A wear particle may be formed due to this this contact, and we can assume that the particle is shaped like a half sphere. That means that the volume of this particle is half a sphere. So it's 2/3 pi a cubic. Okay, that's just an assumption. It's not very critical. It could be something else too, but it's definitely a cubic because it's a volume. Well, now let's assume that not all the contacts give rise to wear particles. That's very a reasonable assumption, because it would be very bad if all the asperity contacts would lead to wear particles. Then the wear should be very high. So let's assume that only a very small fraction, theta in this case, are giving rise to an actual wear particle. Then the average volume worn away per sliding distance 2a. So when you slide a distance of 2a from initial contact to when this has passed completely, then it will has been sliding 2a. You see that a is of course the radius of the contact here. So that will mean the dq, which is the volume for that single particle pair, or the asperity pair, is then the fraction theta multiplied by the volume, wear volume, divided by the distance. So it's per sliding distance here. The volume, we know that the volume is 2 pi cubic A over 3, and you simplify it, you get something like this. This is dq. The total wear rate is then the sum of all the asperity collisions. So it's just the q is the sum of all the dq's. So that is assuming that you have the same fraction everywhere. You also bring the 3 from here, and you have the sum of the pi a squares like this. Okay, but what is the total load then carried by all the asperities? Well, the total load is of course the sum of all the asperity contacts, and assume that the hardness is equal everywhere, it's the sum of the pi a squares then. So that means that the sum of pi a square is the load, the total load divided by the hardness. And put that into the previous expression for the total wear rate, you end up with something like this, that the total wear rate is the fraction theta divided by 3 multiplied by the load divided by the hardness. Now, why having a number 3 there? There is no reason to have that. It comes also from the assumption of creating a wear particle which is shaped like a half sphere. So you may create a particle shaped in any shape. So let's just forget the number 3 and call the theta over 3 to name that, to denote that to k instead. So then you end up with an expression like this. And so this is a k, which is a wear coefficient multiplied by the load divided by the hardness, and that is actually wear volume per sliding distance. So if you want to know the wear volume, you simply multiply this expression with the sliding distance. So this is the typical Archard wear equation. The wear volume is some small number. K is a small number because it has to do something with the fraction theta here. It's a very small number, much smaller than 1, multiplied by the load. So the higher the load is, the bigger the wear is. The higher the hardness is, the lower the wear is. Sounds reasonable. And the longer you slide, the more wear you will get, and that sounds also reasonable. So it seems to be a reasonable equation. Actually, this is the Archard wear equation, but there was a Swedish guy already before Archard. He derived a similar equation, so or the same equation. So some people actually call this Holm's equation. Ragnar Holm was the name of that guy. So the K here is a probability parameter, and the K varies then with different materials, different operating conditions. We can keep on working with this expression a little bit, because we are coming to the PV number then. If we express Archard's equation in terms of the average wear depth, that is, instead of having the wear volume, we talk about the wear depth instead. So we assume that we wear off a layer of the surface. Then you have the volume is the area of contact multiplied by the wear depth. And that is then, again, according to Archard or Holm's equation, kWs over h. But the load is the pressure multiplied by the area. Or since the A is found in both sides of this equation, you can get rid of the area, and the wear depth is simply kps or h. Now if you differentiate, I call it differentiate here, it's not a perfect differentiation with respect to time, because I only differentiate the distance s here, sliding distance s. But if we assume that everything else is constant in time, we can do it like this. Then the the wear rate per time, the volume, the thickness worn per time unit is simply then the k over h multiplied by the p multiplied by the velocity, since the sliding distance time derivative is the velocity. And here you see that the PV number is an important thing. That makes sense because the PV determines determines how much power you put into the surface in a way. So its units are watt per square meter. So the more watt you put into the surface, then the more wear. Sounds reasonable, doesn't it? So of that reason, PV has been used pretty often in tribology. So if you take a bearing, this is a kind of a plain bearing, composite plain bearing. So you don't have any lubrication. In this case, it's just a journal in a bearing, in a bushing. Then you can plot the PV diagram of this type. So you see here that you have P in one direction and V in the other direction, and at a certain number, a certain PV value, P multiplied by V, you reach some end of a possible operation. So if you have too high PV number, you can't really operate it there. And but of course, it's a little bit different if you have high speed and low pressure than if you have high load and low speed. If you have high load and low speed, you are limited here by the strength of the material. The whole bearing may fail because of high loading if you increase the pressure further here. If you are here even at the low load, you can't operate at higher speeds because the temperatures will be very high and you may melt the surface layers here. So, and in between you have something intermediate conditions then. So it's not a perfect limit that PV must be below a certain number, but it's almost like that. And you can see here also in this case that the friction varies with the PV number, but that's a very specific thing that refers to that actual component, in this case an SKF plain bearing. So what's the problem then with this Archard wear equation? It seems to be a fantastic equation. It's simple, it's only a few numbers to put into the equation, but there is a K problem here. The K is an empirical factor. It depends on everything. It depends on so many parameters. It depends on the contact pressure itself, so it's not really linear with pressure, or it's not independent of pressure. It depends on temperature, hardness, lubrication quality, if you have some tribochemical reactions there, if you have some adsorption of some surfactants there, some additives, if it's influenced by the roughness, and if you have some third bodies coming in, wear debris or particles coming in from outside, it's the material types, the microstructure, if you form some layers, so it will change with time also. So it will change with wear itself, and you may change the wear mechanism. So if you had maybe you had mild wear in the beginning, eventually you get fatigue wear or some catastrophic wear type. So the K doesn't describe that really, and during running in the K is also reduced. So it's not a very easy thing to use in that way, but of course you can use a tribo test that simulates approximately your application, and you can find the K from that tribo experiment, and then you can use that K into your approximative simulation of the wear process. So you can do that. So we have done that, and other people do that too. in numerical simulations of wear, so you can gradually simulate how the surface change with time. So it's a kind of deterministic simulation of wear. So if you can compute the contact pressure, then you can compute the wear, because you remember that it's actually, if the hardness doesn't change, if the K doesn't change, it's only the contact pressure that changes. So if you can compute that, it will be possible to compute the shape of the wear scar. You may also need to know the contact temperature, but to start with, you don't need to do that. So it's and then you can, if you have you have some model telling what the K is as a function of a number of parameters, pressure, temperature, time, etc., then you simply just compute P with a contact mechanics tool. Showing you that in next slide here in a flow chart. So you have your tool, you put two surfaces together, it could be two rough surfaces, you compute the elastic plastic deformations and the contact pressures. So then you know the P in all the points in the contact. You apply the wear model, that you know that the wear is simply the thickness of the worn layer during the time from 0 to a certain time t is simply then K over H multiplied by the P. Now the P distribution here, it's a function of X and Y, multiplied by the speed distribution. It could be a constant here, of course. Then you adjust the shape of the surface, of the roughness. You remove material. You may even adjust the K if you have a model for that, but if you haven't, you just use the same K. And you move to next time step. With a new surface, you compute the new contact pressure, you compute the new wear rate, you adjust the surface again, and you keep on doing this from time step to time step, and eventually you can see how the wear scar progresses. So this is something that is doable nowadays, and it is done in some cases. For example, for the wear of a brake pad, could be useful to do that, and some other cases too, but still not very common to use it. This is an example of this using a ball and plate. So you remember a ball and plate, it's the Hertz contact problem, and when you compute the pressure, you get something in the Hertz contact pressure looking like this. In this case, it's a case with about over 1 gigapascal maximum contact pressure. But if we wear off something in the middle here, you don't have a sphere in contact with a plane anymore. So it will change the pressure over time. So this is the simulation of that. So now you see that the pressure is reduced rapidly to a lower level, and eventually it becomes much lower as you get a flattened part of the sphere. So if it was over 1 gigapascal in the beginning, when wear progresses, you are down to maybe 0.1 gigapascal. And this must be you must remember this when you design a wear experiment. So if you claim that you are making your wear experiment at a pressure of 1 gigapascal, you must understand that after some time, could be pretty fast, you are running your experiment at 0.1 gigapascal. So it's this is important for experimentalists in tribology to remember. So that was it about a short introduction to predictions of wear. There is of course much more to say about this topic, and as I said, this is a topic that will be developed very much in the coming 10 years. So hopefully I can make a very much more detailed video in 2025. Thank you very much.